do. So I want to start talking about it. Erase Max and his Crocs. We'll talk about pregnancy length, we'll talk about Mark Spitz and Michael Phelps, we'll talk about IQ, but let's talk about nuts and bolts first, which is the actual standard rule. So we were just talking about the binomial distribution. And I want to talk quickly about why I focused only on that one. You saw how many there were up there, how many distributions there were. I mean, you got the chi-square, you got the hypergeometric, the geometric. There are lots and lots and lots of distributions out there. Why did I pick the binomial? Well, it's the most prevalent, but it's the most prevalent discrete distribution. Do you remember what the word discrete means? Distribution. In this class, we've been using it kind of, we've been taking it for granted. The word discrete, remember what it means in this class? When data is discrete?
You count it.
You count it! Thank you, Erin! That's exactly right. You count it. You count the number of girls you have in your flock. You count the number of times Max gets his Crocs on the correct feet. It's countable data. It's countable data. Okay? What's the other kind? It's been a long time. And we've been mixing and matching this quite a bit. The other is continuous data. Remember how you get continuous data? You don't count it, you measure it. And this is why I want to bring what's called the normal distribution on board. Because the normal distribution is the most prevalent continuous distribution. It's the most prevalent continuous distribution. It's the most prevalent continuous distribution. Binomial is the most prevalent discrete. There are other ones. There are other ones. A lot of those ones I showed you today. Benford's distribution, that's totally discrete, 0 through 9. Hypergeometric, geometric. How many numbers did you get right in Keno? Somewhere between 0 and 20, I'm assuming, depending on what game you were playing. Those are countable. Those are countable. Did you notice on that PowerPoint all of those data sets up there? Length of eye contact time with schizophrenic patients, weights of newborn babies, volumes of gas tanks. Those aren't countable, are they? Those are all measured. IQ is measured. You might not realize how yet. We'll talk more about that on Thursday. Those are measurements. Every single data set up there was a measurement, not a countment. Not countable. Which means you couldn't put them into dist fill, could you? If I asked you for the smallest x, so let's go with weights of a 15-gallon gas tank, and I put smallest x value. I mean, technically speaking, it would be 0, I guess. But then what would the largest x value be? And what would the next one bigger than 0 be? See, this is a problem. This is a bit of an issue. Here's the issue. With a discrete distribution, it is amazingly easy to create a t-table, like we do in dist fill, where you've got an x and you've got a p of x, and you usually start at 0 and go to 1 and 2, and we drop until we get to, I'm going to call it n, whatever we stop at. And then we simply fill in the probabilities, and yay! It's all done. It's all done. It's great. Pretty straightforward. The problem is with a continuous distribution, it's not that straightforward anymore. We need to do this idea. We need to come up with this idea, and we need to do it in a continuous fashion. I'm going to slide over to that board over there. We're going to draw a nice picture over here. That's going to help us.